Hello everyone, hope you are all doing well, and today I will present a new corpus processing and analysis pipeline for Quickref. I'm Antoine Hacquard, a third-year student at EPITA and also a member of the EPITA Research and Development Laboratory, also called LRDE, and my supervisor at the LRDE is Didier Verna. First of all, I would like to introduce you to two Common Lisp tools called Quicklisp and Quickref. Because Common Lisp is such a powerful and expressive language, it is really simple and quick to create your own libraries for your personal project and then to open source it. This expressibility causes several problems, which some tools are here to tackle down. The first problem it causes is that because of the wide diversity of libraries, it can be difficult to install and download some libraries. This is why the Quicklisp tool was created. This tool helps the programmer to download the library and all of its dependencies and then to install it with just one command that you can see in this screenshot. The second problem of the expressivity and powerfulness of Common Lisp is that because it is so quick to create a library, many programmers don't take the time to document their code, and so we had many libraries which are just not documented. So to solve this problem, Didier Verna created the Quickref tool, which aims at automatically generates library documentation for all of the library referenced by Quicklisp. This tool uses an underlying project also from Didier Verna, which is called Declet. This project will generate documentation for every library of the Common Lisp, and then Quickref will aggregate all of this documentation into a single website that you can see in this screenshot. But these two tools doesn't solve the last problem of the wide diversity of the Common Lisp libraries. This last problem is that we need the name of the library to install it with Quicklisp or to see its documentation with Quickref. So a programmer needs to first choose the library he wants to use, and this is why we introduce a new keyword index for Quickref. The idea behind this index is really simple. We want to provide to the programmer an index where he can click on a keyword and see all of the libraries associated to this keyword. The keyword can be, for example, a GUI, website, command line, and then he will see all of the library associated to these keywords. Just a little disclaimer at this point. This index is still a work in progress, and so you will not see it in the Quickref website. I would like in this presentation show you all of the pipeline we realized to create this keyword index and to show you some major change we had to overcome to create this keyword index. So natural questions that you can ask yourself at this point of my presentation is, why not just use a modern search engine to find the library we need? To these questions, we have three answers. First, the search engine doesn't know the Quicklisp availability of the library. So if you want to choose a library, you can prefer to choose a library from Quicklisp because it will be so easier to install than a library from a GitHub or anywhere else. So we think that the Quicklisp availability is a great point in the choice of a library. Then the second point of the why of our keyword index is that because of its design, because it is based directly on the underlying documentation of the libraries, our pipeline will have a natural emphasis on libraries with some documentation. So better will be the documentation of a library, better it will be indexed in our index. And the last point of the use of our keyword index is that the underlying pipeline can be used to create other potential applications and not just to create a keyword index. This is due to its fully modular systems, and it can be used to also create word clouds or statistical or topic analysis, for example, to analyze the Common Lisp ecosystem. Now let's see a pipeline overview. Here is the pipeline we created in order to generate automatically a keyword index for Quickref. So as you can see, this pipeline is based entirely on the corpus of documents, which is composed of all of the technical documentation of all of the Quicklisp libraries. All of this corpus will be then sent to different blocks of our pipeline in order to generate the desired output. If you want more information about this corpus, you can always refer to the paper we published with this presentation. The first block of our pipeline is a block of tokenization and part-of-speech tagging. The process of tokenization is the process of cutting a text into chunks, which can be words but not necessarily. So in this example, this can work. We can cut this text into 4 tokens: this, can, and work. When we have tokenized the whole corpus, we can then use a POS part-of-speech tagging tools to determine the syntactical class of each tokens we just tokenized. A syntactical class can be, for example, a common noun, verb, adverb, etc. So if we take again the example this can work, we will have this will be a determinant, can will be a common noun, the second can which is not the same can will be a verb, and the final token, work, will also be a verb. When we have associate a part of speech to each tokens of our corpus, we then filter only the common noun of our token and then send all of this common noun to the second step of our pipeline. The second block of our pipeline is a block of stemming and lemmatization. These two tools is used to normalize and sanitize tokens in order to regroup all of the form of a word into a single form. The first tool is stemming. Stemming will extract the root of a word in order to regroup all of the words with the same root into just one root. So the root outputted by this tool will not be a real word. So in this example, argue and all of this form will be stem as argue. Another tool to do approximately the same thing is the lemmatizer. The lemmatization process aims at associating the dictionary form of a word to all of its other forms. So if we take the same example, we will have the verb argue. So lemmatization will always output a real word. When we will have lemmatized all of our tokens, we will then send all of these tokens directly to the most important part of our pipeline, which is the TF-IDF part. The TF-IDF algorithm is an algorithm used to determine the importance of a word in a document. It operates in a really simple way. It first will compute two values, the time frequency of a word and the inverse document frequency of the same word, and then compute the ratio between them to output the TF-IDF value. The time frequency TF of a word is the number of recurrences of a word in a document with a normalizing function over it, and the inverse document frequency of a word is the number of documents where this word appears. So the TF-IDF value will be very low for words which appears many times in a document but also appears in many documents, as the word the, for example, but will be very big for words as temperature, which appears many times in a single document. So for example, for libraries which talk about temperature, it will appear many times in its documentation, but because temperature is not a word used in many other documentations, it will have a low IDF value and then a final TF-IDF value very big. So this block is very important for our pipeline because it will help us to determine keywords for each libraries. So thanks to this step, we will choose 3, 5 or 10 keywords by libraries and then send all of these keywords directly to the final step of our pipeline, the aggregator step. The last step of our pipeline aims at aggregating all of the result of the previous step, the TF-IDF steps. So it will take all of the keywords generated thanks to these blocks and it will aggregate them into the desired output. This output can be a keyword index, as in our case, but can also be a word cloud or anything else that you want. So that's all for the pipeline overview, and now I would like to speak about some major challenge we had to overcome. And if you want more details about the pipeline or more explanation on each experiments we made with this pipeline, you can always refer to the paper we publish with these presentations. The first big challenge we want to talk about is the challenge of out-of-dictionary words. An out-of-dictionary word is a word which is not in the dictionary used by some NLP tools. So let's see an example with the lemmatization tool we use in our pipeline. So this is the little pipeline of the lemmatization. This pipeline is based on the pipeline described by the Liras et al. Paper. Its operation is really simple. First, it will extract the root of the word we want to lemmatize thanks to a lemmatizer, thanks to a stemming tool. So in our example, it will take the root of arguing to transform it into argue, and then it will compute an edit distance with all of the words of the dictionary used by the lemmatizer tools. Just to note, in this example, our entire dictionary just have 3 words, argue, cat, and forest. It does not contain other words. So it will compute an edit distance between the root we extracted and all of the words present in our dictionary. So here with argue, cat, and forest. And finally, it will take the word with the biggest edit distance between the root and the dictionary words. So here we will have the word argue as a lemma of arguing. So this process really works well for words which have their associated lemmas directly in the dictionary. So it is the case for the word arguing with the lemma argue. But let's see an example with a word which its lemma are not directly in the dictionary. So the word docstring will be stemmed at the word docstring because it does its own root, and then we will compute an edit distance between this root and all of the words of our dictionary. Because its lemma is not in the dictionary, it will be matched with anything of the in the dictionary, and in this current example, docstring will be matched with the word forest because it has the greatest edit distance over all of the other words of the dictionary. So we will have an outputted lemma forest for the word docstring. So this is really awkward, and it will introduce noise in the rest of our pipeline because the word forest was not in our initial corpus of documents but will be present in our final index. This is a big problem for our pipeline. So we decided to create our own custom dictionary to overcome this problem. So to create this custom dictionary, we first grab all of the words in our corpus and then use an external lemmatizer. In our case, it is the lemmatizer proposed by the Natural Language Toolkit of Python, the NLTK library. And thanks to this external lemmatizer, we lemmatize all of the words of the corpus and use this new dictionary as our custom dictionary for lemmatization. This approach has for the advantage that we know for sure that all words of our custom dictionary will be in all of words of our corpus will be in our custom dictionary. So it is a big advantage because we know for sure that we will not have out of dictionary words. But this approach has also some inconvenience. The first inconvenience is that it requires an external lemmatizer to create this custom dictionary. This is not a very big problem because we just need to create this dictionary once for every other pipeline run, so it can be mitigated by this fact. And the other problem of our custom dictionary is that we don't know for sure if NLTK will lematize all of the words of our corpus. And for example, technical jargon word, for example, docstring, etc., will be badly lemmatized and so also introduce noise in our pipeline. A potential solution of this issue is to test the lemmatizer against all of the CLHS glossary to see if NLTK will badly lemmatize or not all of these words, and then incorporate directly all of this technical jargon in our custom index. The second major challenge we had to overcome is the challenge of aggregators. The aggregator part of our pipeline is the last block, and it is used to aggregate all of the result of TF-IDF into the desired output, which can be a keyword index, a word cloud, or anything else you want. So, for this change, I would like to talk about an aggregator used to generate a keyword index. So, this keyword index has this keyword index has several conditions to be a good keyword index. These conditions are, firstly, the index needs to have 100% of coverage over all of the Quickref libraries. Indeed, we want that all of the Quickref libraries to be expelled directly from a click in our keyword index, and so it is really important conditions. Another condition is that we want the keyword index small because it is not usable to scroll over 2000 keywords to see the keywords you want. And the final conditions we want for our keyword index is that we want a few number of libraries associated to each keyword, because if we have 100 libraries associated to each keyword, it will just be unusable. So our first approach was to implement a histogram over the TF-IDF output to generate a keyword index based on the occurrence of each keyword in the TF-IDF results. So here is a little example. Thanks to the TF-IDF algorithm, we selected 3 keywords per library, for the first library, the second library, and the third libraries, and then we use a histogram over the number of occurrence of each keywords to generate this keyword index. This keyword index is then ranked over the number of occurrence of each keywords. This outputted keyword index has several problems and doesn't meet the 3 conditions I spoke about earlier. So first, histogram, because it favors the words with a great number of occurrence, will create index with a great number of libraries associated to each keywords. Histogram approach will also have a tendency to generate very big index in order to to hit the 100% of coverage. So a histogram is just not usable to generate a keyword index, but the histogram approach is a great way to generate a word cloud. So to overcome this problem, we think about two other potential aggregators. The first one use an approach more top-down, and the idea behind this aggregator is to create a sort of meta TF-IDF over the TF-IDF results. So for each keyword outputted thanks to the TF-IDF blocks, we will compute a pertinence score, which can be anything, but in our example is the average of TF-IDF values. And then we will rank all of the keywords thanks to this pertinence score and select just enough keywords to reach the full library coverage. So if we take again the same example as in the previous slide, you can see that we take the TF-IDF output, we compute the mean of the TF-IDF values for each keywords, and then we rank them thanks to the pertinence scores. Another approach we think about to create the keyword index is an approach more bottom-up. This approach will start with the keywords with the fewest associated libraries and take just enough to achieve the fully library coverage. So this approach will tackle down the problem of a great number of libraries associated to each keywords. But these two aggregators are still work in progress and not implemented in our current pipelines. To conclude, we created a pipeline in order to generate a keyword index. This pipeline is fully modular and is composed of 4 blocks. The first 3 blocks are fully operational, and we plan to release them as independent libraries. But the last block of our pipeline, the block of aggregator, need more work on it. And if you have any suggestion or any ideas about this aggregator in order to generate a keyword index, we will be very pleased to listen about your feedbacks. Thank you for listening, and have you any questions?